Welcome to homework.
Okay, we've got isomers. Constitutional isomers, they're both C5H10. They've each got one double bond. Uh, Compound Y possesses a carbon-carbon double bond that is not stereoisomeric. And there's many different possible structures for compound Y. So let's just start with compound Y. I think that'll be illustrative if we say, okay, we've got a double bond. That's one carbon, two carbon. We've got three more carbons to add in ways that don't create stereoisomers. Well, consider what creates a stereoisomer when you've got cis-trans or configurational stereoisomerism, right? The necessary ingredients are that you have two different substituents. I'll illustrate that with color here on each side of this double bond laterally, right? So if this is a hydrogen and this is a hydrogen, that's not a stereoisomer. There's no cis-trans isomerism, and then it wouldn't matter what's here or what's here. If there's two hydrogens on one side, then there's no stereoisomers because there's no cis-trans isomerism. There's no not stereoisomers. There's no configurational isomerism, right? Because cis-trans isomerism or configurational isomerism is all about comparing the largest chain on one side to the largest or smallest on the other side. And if these two substituents have the same size, there's no comparison that can be made. Okay, so with that in mind, this is a good place to start for a possible structure of C5H10, right? We know it's not supposed to have configurational isomerism, so let's try this. That means we've put two carbons. We've got three carbons left to add, right? So we could say we could say this is a hydrogen, and we've got one, two, three, 1, 2, 3, 4, 5 carbons. So that's a possibility right there, right? That's one possible structure. Let's do the same. But for example, okay, we put hydrogen here, and then instead of putting all three carbons on one side, let's just put two. And that's 4 and 5. All right, that's another option. All right, so there's two possible structures for Y. Okay, is there another possibility where we can put two of the same thing on one side of the double bond, but maybe not hydrogen this time? So let's put a methyl here and a methyl here, right? From here, it doesn't matter what's on the other side because we've got two of the same substituents, the same as we did when they were both hydrogen, right? So we've got 1, 2, 3, 4 carbons so far. So we'll put our third carbon on there, and it doesn't matter if it's up or down. There's no isomerism. If we could just rotate this 180 degrees to get this molecule, right? No cis-trans isomerism there. All right. And then finally, the other way that we can have a lack of configurational isomerism is to have the exact same, so let's say we go like blue and green. Remember, these are representing different substituents. Sorry, actually, that's not the right idea. Let me erase this. The final structure is actually just a repeat of this first one, but we have a branching structure. So it's still hydrogen on the right, but on the left we do 1 carbon, 2 carbon, 3 carbon. There we go. The idea is still the same. We have two of the same substituent on the same side of the double bond, so there can't be any configurational isomerism. Okay, now for X. We know it's in the trans configuration, which means that we've got the largest substituent on, let's say the right-hand side is the opposite side of the largest substituent on the left, right? So if we've used 4 carbons here, let's just add 1 more here, which will force these to be hydrogens. And there we are. That's carbon X possessing a carbon double bond in the trans configuration. And this is probably the only version we can have, right? Because if we try to make this side longer, this will have to be a hydrogen. If we put the chain of 2 on this side, this will just be a chain of 1 on the right-hand side, and that'll be the same molecule. And branching isn't possible for the same reason that if we tried to branch here, this would become a hydrogen, and that wouldn't have cis-trans isomerism. So there we go. This is our only option for X.